This is what, class number 3, and we have 300 students registered in class, of which there are about 60 in the room right now and about 10 on streaming. So I'm not really sure what's happening with the other 240, but it's a bit of a shame that the semester has hardly begun and guys can't even turn up to the class, right? I would expect somewhat better from CMU students. Anyway, topics for the day. We're going to talk about the problem of learning. For the next several lectures, 1, 2, 3, 4, 5 lectures, we are going to be talking generally about the problem of learning neural networks. For today, we're going to cover, just go over some basic mechanisms, the perceptron rule, its application to multilayer perceptrons. There are portions of the lecture, thank you. Yes. Yeah. This is not meant for you. This is meant to point at the board, right? Anyway, we're going to go over some. There are some slides that I will not show. Adeline and Madeline, please go over these because you're going to encounter these in your quiz, right? So, all right, here's the quick recap. What we've seen so far are that neural networks are universal function approximators. They can model any Boolean function, any classification boundary, even any continuous valued function with arbitrary precision, provided the network satisfies the minimal architecture constraints. If the network doesn't satisfy the required architecture constraints, it's not going to be able to model the function. For example, in the case of an XOR, if you just miss one bit, then you're 50% wrong. This is a binary classification problem. You miss one bit, the error rate is 50%, right? So, but that said, under the right conditions, it can model pretty much any function. So here were all these tasks that we saw, transcribing voice signals, captioning images, playing games, so many other things. In each case, you had this box which took an input. It computed an output. And this box is a function. And because neural networks are universal approximators, they can model any function. Do you mind shutting your phone, please? Lady to your right. Yeah. Please turn your phone upside down. Thank you. Right? When you turn your phones and your laptops on, you're bothering me, you're insulting your classmates who are actually paying attention. Don't do that. Right? So here are the questions. We have this box. So take some input. It produces some output. So what are all the questions that we can we can ask? We are speaking of making predictions about a game, for instance. The immediate question is, how do I represent what goes in? How do I represent the state of the game? How do you represent the input to the box? How do you represent the output? Remember, these are functions. They work with numbers. A game board is not a number, right? And then finally, once we've figured out how to represent the inputs and outputs, we have to deal with the question of how do we actually compose the network that performs the requisite function. So for now, for today, we're not going to worry about how you represent the input and output. We're going to focus on how one composes functions. A quick recap again. Here was the original perceptron. It was a simple threshold unit. You took a weighted combination of the inputs. And if that exceeded a threshold, then the perceptron fired. Otherwise, it didn't. But a different way to look at it was that we first computed an affine combination of the inputs. And then subsequently, we put this affine combination through a activation function. In the basic perceptron, this activation function was a threshold function, which fired if the input was non-negative. So a generalization of that, we can replace that activation function with other kinds of functions. For example, a sigmoid. Or we've seen other ones in class, like the ReLU and the leaky ReLU, and so on. So now I'm going to redraw this neuron a little bit. Observe how we've actually represented it. You have a bunch of inputs. You're computing a weighted combination, and there's an extra line going in which represents this additive constant, what we will call the bias, for that factors into the affine value z. Instead, I can represent exactly the same operation like so, I can say that my input x is augmented by one extra component whose value is always 1, and the weight of the corresponding connection is my bias. So both of these are strictly equivalent. Now the reason I'm actually mentioning this is that very often in my diagrams and my explanations I will not explicitly mention the bias. When I do not explicitly mention the bias, it means that I'm using a representation of this kind implicitly. But we're always looking at affine combinations of inputs which always have a bias. If I don't mention it, then it means that it doesn't mean it doesn't exist. It means it's implicit. Now, so we've defined the basic unit. The entire function itself, we saw, must be a network of such units. And what we will assume is that the network is strictly feed-forward. What I mean by feed-forward is that you have a structure of this kind. So observe that all the arrows are directed. So when some input comes in, that input is going to get processed by some neurons which pass it on to other neurons and so on. Any single neuron is going to observe a single input only once. The signal doesn't loop around and come back to a neuron ever. So these are directed networks. Now part of the design of the network, if you want to build a network that computes a function, is the architecture of the network itself. We had a fairly long lecture on what it means to get the right architecture, but the fact of the matter is finding the right architecture for a problem is quite impossible, we will often sort of over-design and have too many parameters. But for the purpose of this lecture, we're going to assume that the architecture of the network is given and has the capacity to model the function that we want it to model. So now this entire network is a connection of many neurons, but it takes an input x and produces an output y. So basically the entire network is just a function. But this is a function with parameters. And what are the parameters of the network? The parameters of the network are the weights associated with each of these connections, or the bias. So observe that I've just included this extra 1 to represent the bias. So the parameters of the network is a set of weights and biases for all of the neurons in the network. And now, if I want this network to represent a function properly, then this means I must set the weights and the biases just right so that the resulting network computes the function that I want. And when I speak of learning the network, I'm really speaking of figuring out what these weights and biases must be in order for the network to compute a specific function that I want it to compute. Right? So questions? No. Okay. So moving on. We've already seen that the MLP can represent pretty much any function to arbitrary precision. Right? But then the question that we're asking today is, sure, I know the MLP can model any function. You give me a function, the MLP can model it. But then how do I figure out what the weights and biases, what the parameters of the network must be in order for it to model this particular function that I'm trying to model? Now, the trivial solution, you can do this by hand. So let's say I want a function that actually produces a 1 when the input is inside the diamond and 0 outside. We spent a couple of classes seeing how we could do this. Here, for example, the diamond has 4 lines of slope 1 or minus 1. And so literally by inspection, I could tell you that this line could be captured by a single perceptron. The input here of course is 2-dimensional, so this line could be captured by a single perceptron whose incoming weights are 1 and minus 1, and the bias term is 1, the bias, not the threshold. This one, because the slope is a negative 1, right? The weights are going to be minus 1 and the bias is 1. This guy would be, again, minus 1 and 1, and the bias is 1, minus 1 and 1, the bias is 1. So you can actually literally, I'm not going to derive this, but you know how to do this. You could actually compute this guy, and you could design the network by hand, and it's easy enough to do so for something of this kind. In previous classes, I've also sort of gone through the exercise of trying to get you guys to design a network for me that can perform simple addition. It turns out it's very complex, but you can actually do it. The problem is, if you're using this construct by hand option, when you want to handcraft a network to compute a specific function, this is only going to be feasible for the simplest functions. Anytime the function goes beyond basic simple operations, this is out the window. So while it's technically a feasibility, practically it doesn't make sense. So what we really need is an automatic technique for estimation of these parameters, for estimating an MLP. So more generally, what this means is that you're given a function g of x, and we want the network to actually compute this g of x. So we're going to have to derive the parameters of the network such that this g of x is computed. Now, how can you actually learn this network? The way we will do it is we will sort of optimize. Now, again, remember that we are assuming that the architecture of the network is given to you. So we know the parameters, right? And now, where did I put my chalk? Yeah. So what you really have is this is a one-dimensional illustration, x. Here's a function that you're trying to model. Now, if I set the parameters of the network to any value, it is actually going to compute some function. And that function may not be the function that I want. So that function may be something like this. And so now, at each point, I can define, at each x, I can define some measure of the error between what I want the function to compute and what the function actually computes. So the total error over here, of course, is this entire area. And if I modify the parameters of my function, this area is going to change. So if I had a different set of parameter weights, the function might be like so, for instance, in which case the error is even smaller. And so the question now is, how do I choose my weights such that the area of this error region is minimized? Now I'm going to quantify this error at any point through a divergence metric, or a divergence function, which may not be a metric, which basically compares the function value of the function that I really want, which is g of x, against the value that the network currently gives me, which is f of xw. And it's this quantity that I'm integrating over the entire space, and I want to minimize this metric of the error between what the network is actually computing and what I want it to compute. All clear, right? Problem. This is assuming that the function g of x is known. In reality, g of x is not going to be known. So if I'm asking you to play chess, right, nobody has defined the correct move for every single state of the chessboard. It's just not feasible. You don't know the function. You cannot compute this integral because the value of the function is not known for nearly all x. So what we will do is to sample the function. Instead of having the value of the function, I wish I had a chalk of a different color. So what? So if I have a function, instead of knowing the value of the function at every point, I'm actually just going to sample it. I'm going to pick a bunch of x's and read the value of g of x, add those x's. Basically, we are getting input-output pairs for a number of samples of x. And the manner in which we choose these x's, at which we are computing the output, if you do it properly, you are going to choose more x's where x's naturally occur more frequently. So the sampling of x must follow the actual distribution of x. Now, gathering such input-output pairs is really trivial. This is just collecting training data. For example, we're gathering a set of images and their labels, so their captions, gathering a set of voice samples and their transcriptions. So this is not hard at all. And now, you don't really have the entire function anymore. You just have these guys. And from these guys, these training samples, you have to learn the function. So what we want to do is to estimate the parameters. Now, at this point, observe that the rest of this is just really not known, right? Although this function exists, this stuff is not known. So you only have these few dots. And what is the best you can do when you only have these dots? You can learn the parameters of the network to fit these values at these x's. And if you learn the parameters of the networks to correctly compute the g of x values at the given x's, you can hope that afterwards, over the entire space of x, the function that it learns is actually the correct function, but there is no guarantee. Make sense? Right. So this is really what we're going to do. So the story so far, learning a neural network is the same as determining the parameters of the function, the weights and the biases, required for it to model a desired function. And the network itself must have sufficient capacity to model the function that we're interested in. Ideally, we'd like to optimize the network to represent the function everywhere, like in this example, right? But in practice, this requires knowledge of the entire function, the function over the entire space. In practice, we don't really have it. So in practice, what we will do is to draw some input-output pair samples, and we're going to estimate our functions we're going to optimize our function, our network, to compute the target output values at the samples that we've drawn, and we're going to hope that it fits the function properly. Okay? So let's start with the simplest possible function. We know that these things can model classifiers, multi-class classifiers, logistic, real-valued functions, anything. Let's begin with a simple classifier. It's better than regression. And in fact, even historically, classification was one of the earliest problems, actually addressed using multilayer perceptrons. And specifically, we'll consider binary classification. So taking a step back in history, the original multilayer perceptron, as proposed by Marvin Minsky, was just a network of perceptrons with threshold activations, the basic perceptron. And we want to compute this using only training instances of input-output pairs. Now, place yourself in 1965. This we know, even with the threshold functions, we know this function can model pretty much anything, right? So now you want to learn it. How are you going to learn it? And what is the simplest multilayer perceptron you can think of? Pardon me? Something even simpler, right? Just a single perceptron. The simplest network you can think of has only one unit. So this is a step function across a hyperplane. So let's look at the problem of learning this function. But our setup is that the function, we are not going to be given the function itself. What we are going to be given is a collection of training samples. You're going to be given the information that for all of these red dots, the output must be 1. For all of the blue dots, the output must be 0. Learn the function, right? It's a single perceptron. So basically, based only on those dots that you have to learn the parameters, the weights of these inputs and this bias, which are basically learning the parameters of the hyperplane itself, right? Okay. And so again, what this means is that you want to learn the weights and biases such that they represent a hyperplane such that all of the red dots are on one side and all of the blue dots are on the other side. The answer may not be unique because the dots do not span the entire space. So which again tells you that, for example, there's no guarantee that you're only going to learn this function exactly. You can learn others which have an error with respect to the target function, but which are still correct at the dots itself. So let's restate the perceptron. I'm going to restate it slightly differently. Instead of having a bias, I'm going to extend the input with this additional component whose value is 1, such that now I can rewrite the function for the perceptron as this over here. The output is 1 if the weighted combination of inputs is non-negative and 0 otherwise. Observe that I have gone from being affine to being linear. And you all know the difference between affine and linear at this point, right? So this is just for convenience, nothing else. Okay. Now, first thing, Remember, a perceptron is completely specified by a hyperplane, right? Now let's assume the hyperplane is linear, it's going through origin, keeping in mind that this really is no different from an affine hyperplane, right? So if that's the case, then what is the equation for the hyperplane? We can write it like so. We can say summation wi xi equals 0. This is the equation for the hyperplane, right? I can put all of the w's in a vector, w1 through wn, wd. I can put all of the x's in a vector, x1 through xd, d being the dimension. And I think I've represented it as n plus 1 on the slide, but it's the same thing. And now my equation for the hyperplane is w transpose x equals 0, right? The inner product between two vectors is 0. Now when I tell you that the inner product between two vectors is 0, what can you tell me about the angle between the vectors? Anyone? So what's the angle between the vectors? You. The brown shirt guy. Yeah. 90 degrees. Answer, man. You help me over here. I'll wait for you, all right? So now, what does it mean for me to say w transpose x equals 0 is the equation for a hyperplane? Can you tell me? Anybody else? Yeah. Basically, it's the locus of all vectors that are perpendicular to the weight vector. If I give you the weight vector, thank you, what's your name? I can't hear you, and I don't think I'd be able to pronounce it. We'll catch you later. Anyway, so if I give you a weight vector, W, right? There are some vectors, now in, say, let's say this three-dimensional space, there are many vectors which are orthogonal to this W, right? And so W transpose x equals 0 is the equation that represents every x that is orthogonal to W. It's the equation for a hyperplane, and specifically the weight vector is normal to the hyperplane, right? So this is something you want to remember. If I have W transpose x equals 0, that is the equation for this guy, which is the set of all vectors that are orthogonal to W, and the weight vector is normal to the hyperplane. Now consider any vector on this side of the hyperplane, the same side as the weight vector. What is W transpose x for this one going to be? So let's say this is x, right? I can write x as x1 plus x2, correct? Is x1, what is the relationship of x1 to W? It's orthogonal, correct? So what is W transpose x1? 0. What is the relationship of x2 to W? It's parallel. So what is the sign of W transpose x2? Positive, correct? So which means that any vector, any point which is on the same side as W, is for those points, the inner product between the weight vector and x is going to be positive, right? What about something on this side? This one can be written as this plus this guy, right? It's opposite to W. What would be the inner product between the weight vector and this one? Negative, right? Because once again, it can be written as the sum of two components, one that's on the plane, which is orthogonal to W, and the other which is parallel to W, but it's pointing the other way. And the inner product between two vectors which are 180 degrees opposed is negative, right? Remember, again, W transpose x equals mod x, length of x, length of W, cos theta. If theta is 180 degrees, that's going to be negative, right? So this we remember. Now, when I say I want to find a hyperplane, when I want to learn the perceptron, I'm saying I want to find a hyperplane that perfectly separates all of the points for which I have labels. In other words, I want to find the weight vector such that all of the positive points which have label 1 have a component that's parallel to the weight vector and in the same direction as the weight vector, and all of the instances that have a label -1 have a component that's actually opposed to the weight vector, right? So we want to find the weights vector such that W transpose X is positive for all the red points and negative for all the blue ones. How can we do this? Turns out there's a very simple algorithm. We're going to, it's iterative. You're going to start off with some W, and you're going to only update W on misclassified instances. If the instance is misclassified, and if the misclassified instance is a positive instance, you're going to add it to W. If it's a negative instance, you're going to subtract it from W. And we'll see this pictorially, but I can rewrite it like so. Mathematically, it's convenient for me to write the labels as +1 and -1 rather than 1 and 0. So all the positive instances, the red dots will have a label of +1. All the blue dots will have a label of -1. And then I can go through all of my training instances, and the classification rule is going to assign a label that's simply the sign of W transpose X. We've already seen this, right? And if this is incorrect, then to the weight vector you're simply going to add Y times X. Now this doesn't give you a lot of intuition, so let's do this with figures, right? I have a collection of these red and blue dots, and the red dots have a sign +1, the blue dots have a sign -1. I start off with an initial weights vector. The initial weights vector represents some arbitrary hyperplane. Now if I'm treating my weights vector as representing a classifier, so the hyperplane that the weights vector represents should have the property that all the red dots are on the same direction as the W from it, and the blue dots are on the other side, right? So in other words, you want all the red dots to be on the plus side of the hyperplane, all the blue dots are on the minus side. Now when I arbitrarily choose a random hyperplane, this is not going to happen, right? So here for instance, so this is my initialization. Here for instance, this blue dot, which should have, I've flipped my signs, beautiful. So my blue dots are +1 and the red are -1 in the example. Apologies, but let's stay with this, okay? So this blue dot must have a sign of +1, but it actually has a sign of -1, right? Now consider an individual dot, right? Just think of, why does that happen? You need handles. Consider an, okay, does anybody see my chalk? Okay. Consider an individual dot. Suppose I have a dot and this has a label +. If this is the only dot that I want to represent, what is the ideal weight vector? Anyone? If this has a label, yeah? The vector to the dot, right? This guy is the ideal weight vector. That's going to give me this hyperplane, right? Any other weight vector is actually going to make the dot closer to the boundary. Correct? Suppose I have a dot which has a label -, then what is the ideal weight vector? Yeah? Pardon me? No, I don't have this dot. Just I have only this one dot. Then what would the ideal vector be? So this, if I had the weight vector this way, it's going to label it as +1, right? I just flip it. The negative of the dot, that is going to be my ideal weight vector. Correct? So we recognize this. This is easy. Now let's go back here and see what happened to this one. This guy should be a plus, but it's been labeled as a minus. So the obvious thing for me to do is to move my weight vector towards the ideal weight vector for that dot. Correct? Which would be for me to simply, so the ideal weight vector is this guy for that dot alone, I'm just going to add it to my current weight. And that's going to swing the boundary around like so. And now I've corrected it, right? But then after having done this, now that point is maybe on the correct side of the plane. But we're not done. This dot is misclassified. This dot is a negative instance, which is being classified as a positive instance. What is the ideal weight vector for this dot? Pointing in the exact opposite direction, right? So we are going to add the ideal weight vector for this dot to our current weight. So that's the vector here. We'd flip it and you add it to the current weights vector. And that's going to be the resultant weight vector, and that's your boundary, right? New boundary. And now everything is correctly classified. We are done. You can't do any better. So the algorithm itself is very simple. You can make it sound complicated when you write it down in formulae, but the intuition is trivial, right? So this was the one that Rosenblatt came up with way back when. And so long as the red and blue dots are perfectly separable by a hyperplane, you can always find a hyperplane using the perceptron algorithm. This is guaranteed. Not only is it guaranteed that you can find the hyperplane, if, again, dependent on the dots being separable by a hyperplane, you actually have an additional guarantee which says that you're going to find the ideal hyperplane in a finite number of steps. It's linear in the number of training points. Let me skip the text. So let's look at the figure. Now here are all of these dots. Now the dot that is farthest from the origin is this guy. So the length of the largest training vector is some gamma, right? Or some r. And then there's also the best case decision boundary between the two classes, where the two classes are as far apart as possible. This is the margin of your support vector machine, if you're familiar with SVMs, right? That is the best case distance of the worst case points from the boundary. So it turns out that the algorithm, the number of misclassifications, the number of updates that the algorithm will take in order to converge is upper bounded by the ratio of r and gamma. And because both of these are finite, literally there's a finite number of steps in which the algorithm will find a solution. So this is very nice. For the simplest possible problem, we found an algorithm that can actually find the boundary, provided the classes are separable. And the way we did it was to start off with an initial guess and keep making small adjustments to it anytime we got a point that was misclassified, right? Now can I take the same algorithm one step further and try to do this for a more complex problem like this one? Now here is the boundary that I'm trying to estimate. I want to find this double pentagon. I want the network to fire if the input is inside the yellow region and give me a 0 or a -1 if the input is outside. Except I'm not being given the double pentagon, I'm only being given the red and the blue dots. Now observe that a solution exists. A perfect solution exists for this setup, right? So using the same intuition as we did in the perceptron algorithm, we should be able to use something like the perceptron algorithm to find the solution for this problem, right? Now, assume that you're using the perfect architecture. So we have a network which we know can solve this problem. We are given the red and the blue dots. We are going to try to learn something like the perceptron algorithm to learn the solution. Now, if we do this, what is it we really need to do? What we are really trying to do is learn all these boundaries. We know, for example, that if I have this double pentagon, if I have this double pentagon, then this first neuron to the extreme left is probably going to have to model this boundary, correct? The second neuron has got to model this boundary. and so on. Each of the neurons in the first layer is going to model one of these lines. And now, so the lower level neurons are all linear classifiers. It's their combination that's giving you this nonlinear output, right? But here's the problem. The training data that you actually have these labels. The reds are 1s and the blues are -1s, right? Now, you want this perceptron, say you want to learn this. No. I'm using a different example. So let's say I want to learn this boundary. If I want to learn this boundary, what are the requirements on the labels of the dots on either side of the boundary? For the perceptron algorithm, we said it can only learn the linear boundary if the dots are separable, right? Which means I want all of the dots on this side to have the label plus, and all of the dots on this side to have the label minus. If I don't have that, it's not going to be able to learn this boundary, correct? What are the dots labels that have actually got? Many of the dots on that side have the label minus, right? Similarly, if I'm trying to learn this guy, this is even crazier, right? I want everything on one side to be plus and everything on the other side to be minus. You have pluses and minuses on both sides. So you're not going to be able to, from this basic labeled data that you have been given, you're not going to be able to learn this function. Because what this particular perceptron requires is labeling of this kind. So what is the solution? Here's the crazy bit. You're going to have to figure out what is the actual label you must assign to every single training instance, because you don't really know, in order to learn every single perceptron. Now you have n training instances. How many ways can you assign binary labels to n training instances? 2 raised to n. So you're going to have to evaluate every one of these 2 raised to n possible ways of assigning labels to these instances just to be able to learn one boundary. And how many boundaries do we have here? 10 in this case, correct? So what happens is, for a single line, you have to try out every possible way of relabeling the dots, not just the blue dots, both the blue and the red dots, right? And in fact, we have to do this for every one of the lines. And we have to figure out how to relabel all of the training data to learn every one of the lines, such that when they are combined, the resulting output is exact for what you have. And observe that this is true even for a problem where the data we know are can be perfectly separated by this network. We have data for which a solution exists. We have a network of the correct architecture. But using something like the perceptron rule, where we start off with some initial guess and then we readjust things every time you find a misclassified point, is simply not going to work, because in addition to learning the weights, you're actually going to have to learn how to relabel the points for every single line. This is an NP, right? The problem has this solution it's feasible, it's theoretically possible. It has exponential time complexity. Right? So this is where we were in 1968. We knew that these things could model functions. We knew solutions could exist, but really we didn't have the mechanism to actually find these solutions, because the solution had exponential complexity. So obviously people don't give up. So there were greedy algorithms proposed by Bernie Widrow, Adeline and Madeline. Widrow is a professor over in Stanford, and the learning algorithms he came up with have formed the basis of a lot of machine learning and signal processing. So what we figured was that the perceptron learning algorithm cannot be directly used to learn an MLP because of the exponential complexity. So can we use greedy algorithms instead, where we sort of flip one, the problem here is you had to figure out the labeling for the entire training set for each perceptron. Instead of doing that, can you do this by flipping one training instance at a time and figuring out what really happens? So these algorithms were called Adeline and Madeline. We won't go through this in this class, but they are on the slides. They do feature somewhat extensively in your quiz, so please go over the slides, right? But now, so to summarize everything we've seen so far, learning a network is learning the weights and biases to compute a target function. In practice, you learn networks by fitting them to match the input-output relationship of a finite number of training instances. A linear decision boundary can be learned by a single perceptron with a threshold function activation in linear time if the classes are separable. Non-linear decision boundaries require networks of neurons. Training an MLP with a threshold function activation perceptrons will require knowledge of the input-output relation for every training instance, for every perceptron in the network. And since you don't have this, these must be determined as part of training. And so in fact, turns out it's not just, it's NP-hard. The problem is NP-hard, and I believe NP-complete. So here's where it was. The realization that training an entire MLP was a combinatorial optimization problem stalled development of neural networks for well over a decade. Paul Verbos finally found a solution for this in 1974 in his PhD thesis in MIT, but the world didn't really discover the solution for another decade. Now, why do we have this problem? So let's go back and consider the single perceptron, right? If I'm considering the single perceptron, now let's say that figure is maybe a bit confusing. I need a duster with a handle. So now let's say I have these pluses and I have these minuses in my training data, and my initial decision boundary, this is the weight, is like so. Okay. Now this is wrong. It's got half my things wrong, right? Now suppose I know it's wrong, so I decide to adjust it. And if I adjust it to this one, just move it, is my error going to change? No, right? Suppose I adjust it instead to this one, is my error going to change? Again, no, right? So simply by inspecting how the classification changes when I modify my parameters a little bit, I will not be able to decide which direction the parameters must be modified in. This is and this is why I cannot use simple adjustment-based algorithms with a network, right? So in fact, you can vary the weights a lot. You can swing a network. You can swing this one from this guy all the way out to this guy, and the output is really not going to change. You can vary the weights a whole lot and observe no change in the output. Same thing here. So here, for the individual neurons, you have the same problem. You have many neurons, right? And for each one of these, I can vary the parameters a whole lot, the decision boundary a whole lot, and still not see any change in the output, which doesn't tell me which way to vary the parameters. Now, in order for me to be able to learn the network properly, what I need is some setup where when I change my parameters a little bit, I want to see whether the error is increasing or decreasing. If I can do that, then I will keep inspecting the various changes and keep adjusting my parameters in the direction where the error is decreasing. Make sense, right? So this is really what we want, and this is not going to be feasible with this kind of activation function. Well, there's a second problem. The second problem is that we assumed all the data are nice and separable. In practice, that's not going to happen. You're going to have blue dots on the red side, red dots on the blue side. So the Rosenblatt's perceptron would not even work in the first place for this kind of data, right? So what is the solution? What we will do is to replace the threshold activation with a continuous valued activation. Now observe what happens in this example. If I have just over here, so let's say I have these pluses and I have these minuses, and I have this as my boundary, right? Now if I'm calling this my positive side, so my sigmoid goes like so, right? Coming out on the the shape is actually coming out of the board. Now, when I swing this thing towards this guy, you can see that the positive is going down the slope. So the label that I am assigning to it is moving away from the correct value of 1, right? On the other hand, for this guy, I can see that it's actually in one direction. I'm getting myself tangled up, but that example is a bad one. But what you would see is when you have a continuous valued function of this kind, as you move it, then the gap between the label that you want, which is +1, and the actual value that the function outputs, which is going to be anything between +1 and -1, that's going to change. So this gives you some mechanism for if the activation function is continuous and differentiable, you can actually see that I have this sigmoid, and here I have a training instance whose label should be -1, but it's actually being assigned as +1. If I move the sigmoid a little bit this way, what happens to the label? And you can see that the label assigned by the network is actually, the value is actually going down, which is closer to the -1 that I want it to be. And so now I know that it's the correct thing to do is to move it in this direction. Whereas if you had a perfect threshold function, sliding it left and right is not going to give you that information, right? So you want continuous functions with continuous variation, which actually give you this information. And one of the most popular such functions, we've seen a bunch, but one of the more popular ones is the sigmoid. And the sigmoid in particular has a very interesting interpretation. So to see what the interpretation might be, let's go back and look at our data. Let's look at non-linearly separable data. Here is a two-dimensional example. You want to classify the red dots as 1, the blue dots as -1 or 0. But you have some blue dots on the red side and the red dots on the blue side, right? So which means I cannot actually draw a boundary which cleanly separates the red and the blue dots. Now to understand this better, let's look at a one-dimensional example. Here is what a one-dimensional example is going to look like. You have blue dots, you have red dots, but there's no distinct boundary where the dots go from being blue to red. As you go from left to right, the number of red dots that you encounter keeps increasing. Eventually you're going to see mostly red dots and almost no blue dots. So instead of thinking of this as just trying to find a perfect bound as representing the data itself, now let's begin counting things. Let's look at a small window around each training point and compute the average value of all the training points within that window. What does this average tell you? It tells you what is the probability of +1 within that small window, right? So within that small window, if you have 6 1s and 4 0s, the average is 0.6, which is basically saying that in this value of x, in this range of x, the probability of the output being +1 is 0.6, right? And as you keep going left to right, and what you will find is initially it's dominated by the blue dots, so the probability is going to be close to 1 for the blue dots, 0 for the red dots. And then as you keep going right, the average is going to slide from blue to red, and eventually you're going to have all reds, right? And so this curve actually represents the probability of class value 1 at each x. And this curve has, the shape of this curve typically tends to look like a sigmoid. And as it turns out, the sigmoid function, which is 1 over 1 plus e raised to minus x, models this shape very nicely. You'll observe that when x is plus infinity, e raised to minus x is 0, so the value is 1 over 1. When x is minus infinity, e raised to minus x is infinity, so 1 over infinity is 0, right? So it actually kind of smoothly slides between the two. And that's not just in one dimension. In higher dimensions too, if x is a two-dimensional variable, you're actually going to get the sheet which has a sigmoidal shape. And if you look at the sigmoid computed over the affine combination of the inputs, that's going to have exactly the shape that you want. So we'll sort of revisit this topic of what the sigmoid activation means, and the fact that perceptrons with sigmoidal activations actually model class probabilities much later in the course. But for now, let's go back to our basic problem. We've replaced the threshold activation with a sigmoid. The sigmoid is differentiable. Now, the sigmoid is differentiable. What it means for a function to be differentiable is that it tells you how much a small change in the input is going to compute, is going to affect the output. That is the notion of differentiability, right? So which means that over here, if I have a sigmoid sigma over here, I will be able to figure out how much a small variation of z is going to vary y. Now, this component is just a simple addition. Z is an affine combination of the inputs. So because it's an affine combination, I can already easily compute how much a small change in w is going to change z, or how much a small change in x is going to change z. So now I can chain these up, and I can tell you how much a small change in x is going to change z, and that change is going to be small. But I also can compute how much a small change in z is going to affect y. And so as a result, I can tell you how much a small change in x is going to change y, right? So by making the activation differentiable, I can actually tell you, we can compute the effect of small variations of either the inputs or the weights on the output. So when you plug this thing into a complex network, now each of the activations is differentiable. So for example, if I wanted to find out how much a small change in this weight is going to affect the final output, now a small change in this weight is going to change the output of this neuron, and because the activation is differentiable, I can compute that. And now I can also compute how much a small change in this guy is going to change the outputs of these two guys, which are the ones that it's connected to. And I can also compute how small changes in the outputs of these guys is going to change y. So as a result, I can actually compute how much a small change in a single weight is going to change the output of the network. And I can do this for every weight in the network, simply because the activations are differentiable. In other words, the entire network is a differentiable function, and it's differentiable with respect to every parameter in the network. And differentiability basically tells you how much small changes are going to affect the output. And once I know that, now I have the handle, the ability to make corrections to each of these parameters to make the output as correct as possible. And so this overall function that we've got is differentiable with respect to every parameter. Small changes in the parameters result in measurable changes in the outputs. And we're going to see exactly how, what these changes are going to be. We're going to derive it later. But then here is the overall setting for the learning algorithm for the MLP. You're now going to be given a collection of input-output pairs, x's and d's. X is the input, d is the desired output for that input. And we now have to find the network parameters such that the network produces the desired output for every single input. We are assuming the architecture is given to us. Now remember again, our original objective was to try to model this function correctly everywhere. If we were given the function, then what we would do was to compute the area of the error between the actual output of the network and the target function. And in the ideal case, what is this area going to be? 0, right? But more practically, because we really don't know the complexity of the architecture required, and our learning algorithms are themselves going to be kind of less than perfect, the error will not go down to 0. So in that case, we're going to impose an extra requirement. We want to say that the regions of the input space which have higher probability must have lower error than regions of the input space which have lower probability. So for example, if you're trying to model this function, right? And then you know that in reality, these values of x are never observed then what would the point be in trying to expend effort in trying to make sure that the function is perfect over here as well? There's really no point, because you're never going to use those regions of the function, right? So to account for this, we will actually weight every value of x with the probability of x. So in other words, we're going to emphasize more frequent values of x more than the less frequent values of x when you compute the error. And this is the error that we're going to try to minimize. We're going to try to find the parameters w that minimizes this weighted error. Now what is this one? This term here is simply the expected value of the divergence, right? Anytime you compute the integral of some f of x times p of x, you're really computing the expected value of f of x, right? This is the expected value of the divergence. That's what we're going to try to minimize. But as we saw, in reality, we are not going to get the complete function g of x. We are only going to get samples, input-output samples. And so we have to estimate the function from these samples. So what do? We want to have, again, drawing this function. In reality, if this is our function and this is our current estimate for the function, we want to minimize this area, right? But we don't have the function everywhere. We only have the function at some locations. So maybe we just have these as our training samples. So all we have are these guys, right? So we cannot compute the area. So instead of computing the entire area that we're trying to minimize, what we are going to do is to try to find the average of these lengths. And the average of those lengths is going to be our proxy for the area that we are trying to minimize. So what we will compute is an empirical estimate. We want to ideally minimize the expected error, what is also called the risk, when we learn the parameters of the network. But we cannot actually compute the expected error. Instead, we will compute an empirical average of the error across your training points. And this empirical average is going to be our proxy for the error. Keep in mind again that the actual objective is to minimize the expected error. It's just that we cannot compute it, so we're going to minimize the empirical average or the empirical risk. And so the business of training a network is really a case of empirical risk minimization. We have a bunch of training instances. We're going to define the error on the ith training instance, which is this, I should have had color, which is this length over here, or some measure of this length, which is the difference between what the network currently computes at that x and what you want it to compute. And you average this over all of the training instances. That's your empirical average error or your empirical risk. And we are going to estimate the parameters to minimize this empirical risk. Right? So observe here that what you're really trying to minimize is a measure of the error between the actual output of the function and the function that you wanted and the value you want. Terminology in the literature is called this a loss for various reasons that I won't get into. So during the rest of this course and in your homeworks, you will hear the term loss, but the loss is simply the empirical average error across all of the training points. Right? So repeating the problem statement again, you're given a training set of input-output pairs of this kind. You want to learn the parameters w to minimize this loss term, which is simply the empirical average error across all of your training points. This is a problem of function minimization. It's an optimization problem, right? So the story so far, we learn networks by fitting them to training training instances drawn from a target function. Learning networks with threshold activations requires solving a hard combinatorial optimization problem. So instead, we use continuous activation functions with non-zero derivatives to enable us to estimate network parameters. And we define a differentiable divergence function. Again, the divergence function which computes the error between the actual output of the network and the output that you want, that must be differentiable, because if it's not differentiable, again, everything is lost. So maybe that's worth explaining. So what you really have is this. You have a network. And what we've done when we made the activations differentiable is that we figured out how much, we made it such that we could compute how much a small change in this weight is going to change the output. But that by itself is not sufficient, because what we are really doing is comparing this output to a desired output to compute an error. If this comparison function, and you want to figure out how to adjust this weight W such that this error is minimized, right? So in other words, the error must be differentiable with respect to the weight. That means this comparison function, this error function itself must be differentiable. So it's not sufficient for the activations to be differentiable. Even the divergence function that compute that quantifies the error between what the network actually computes and what you want it to compute must also be differentiable, right? So, but having said all of that, now the problem can be said as a case of empirical risk minimization, which is a special case of function minimization, right? Questions on Piazza? No, okay. All right, so, yeah.
Since it's an empirical estimation, do we also assume that our training samples, like the distribution of the training sample, actually reflect the actual probability?
Yeah, that is correct, right? We made that statement early on. If it doesn't, then all bets are off. So you really want to sample according to the distribution of the data itself, because that's how you make sure that you'll make less error in more populous areas and more at the expense of less populous areas. Yeah.
So what's the best situation using other activation functions?
Pardon me, could you repeat that?
So what's the best situations if you're using other activation functions?
So what do you mean by using other activation functions? So in all of these cases, the question is, what is the situation when we use activation functions besides the sigmoid? It doesn't really matter. The criterion we want is the activation function must be such that we are able to quantify the change in the output of the neuron in response to small changes in the input or the parameters of the input. And when you're using something like ReLU, where the input falls on the negative side, on the 0 side, at that point the derivative becomes 0. And so, and anytime the input falls squarely in the area where the output is flattened out, you really cannot figure out how much a small change in the input is going to change the output. That's one of the deficiencies of the ReLU that we mentioned in the last class. But if you have a large enough network, some other neuron is going to capture that information anyhow, hopefully. Yeah.
So in that case, is that you're saying that using a sigmoid is always better than using other active?
No, a sigmoid we said was really not a very good function, right? In that as you go far away from the boundary, it flattens out. But something, for example, like a leaky ReLU or many of these other activations which continue to have derivatives, non-zero derivatives far away from the boundary, are obviously going to give you more information, right?
But you're saying a sigmoid is always better than a ReLU?
No, we're not saying that at all, right? We're saying that a sigmoid, so a sigmoid has this property. It flattens out far away from the boundary. So over here you really don't, where a ReLU only flattens out in this region, right? All right, so let's, yeah.
Since the ReLU is not differentiable at 0, so for like small values of the input to the neuron, does it cause problems?
It doesn't have to be strictly differentiable. Even if you're over here, right, what you really want to know, if you're very close to this guy, the odds that you'll fall exactly at this point are very small. But here you really want to compute whether a small change in the input is going to increase or decrease the output. So that you can use any derivative which falls below the function, something called a subgradient, and you can use those values. All of them will inform you that if I increase the input a little bit, the output is going to increase. Anything that informs you of that can be used. Right? Yeah. So the question was, how do you deal with the fact that the ReLU is not differentiable at 0? You don't really, again, the fact that it's not about differentiability per se. It is about the ability to know how much a small change in the input, in which direction a small change in the input is going to change the output. Right? So we can use subgradients. Anyway, moving on. I'm not going to finish today's topics, but what do you understand by the term derivative? Anybody want to answer me? So when I say derivative, what do you think? How do you understand it? The slope at a point. Yeah. What is the slope again? Pardon me? A tangent to the locus.
The rate of change of the output with respect to the input.
Now rate of change of the output. Now you're thinking of a scalar function, are you not? But if I have multidimensional inputs, then what does it mean? So anytime you're speaking of when you're speaking of derivatives, your standard assumption about derivatives is that you're talking about a scalar function with a scalar output. But a better way, and possibly the only useful way to think about a derivative is this. Let's say I have a function y equals f of x. Then if the function is smooth and continuous, at any point when you get close enough to the function, it's going to look like a plane. And so for such a function, you can always ask, how much does a small change in the input delta x change the output delta y? And if it's planar, that's going to be a multiplicative term, right? So the derivative of a function is this value alpha that multiplies a small change in the input to give you to tell you what the change in the output is going to be. And this is really the only way to think about derivatives in any useful way, right? So over here, when you're thinking of a scalar function, you can begin talking about the slope, right? So how much does a small change delta x change y? So what is the relationship between delta y and delta x? Assuming the relationship is linear, then you can sort of write it as the ratio of delta x and delta y and delta x, but you're really speaking of infinitesimal changes. So we sort of like to write it as dy over dx, which is really a very horrible notation for many reasons, because once you go into multidimensional data, you cannot write things in this manner. A more appropriate representation is f prime of x, which we use all the time, right? But the thing I want you to remember is this guy. The derivative is a multiplicative term which tells you what you must multiply an incremental change in input by to compute the corresponding incremental change in the output, right? So why am I insisting on this? Let's go to a multidimensional function, say a multivariate scalar function, where it's a function of the y is a scalar and x is a vector. So like a bowl, it's a function of two variables, right? Now in that case, I can still write delta y equals alpha delta x. X is a vector. Now if I assume x is a column vector, what is the shape of delta x? That is also going to be a column vector, right? It's a small increment. What is delta y? Scalar or vector? It's a scalar, right? So what must this alpha term be? Vector. What kind of vector? Pardon me? Same dimension shape? It's got to be a row vector, correct? If delta x, again, there's a business of a notation. If you think of your inputs as row vectors, then delta y is going to be a column vector. You're going to right multiply it. If you think of your input as column vectors, delta y is going to be a row vector. You're going to left multiply it. So just thinking about it in these terms immediately begins informing you about how you even represent these things, the dimensionality, etc. Right? The key piece, I'm going to assume that my inputs are column vectors. The key piece is this relationship. Okay? Now, once I write it like so, you can see that this alpha is going to be a row vector with many components, right? And specifically delta y is going to be, because it's a component-wise multiplication and summation, delta y is going to be alpha 1 delta x1 plus alpha 2 delta x2 all the way to alpha d delta xt, right? Now I can ask myself, delta x is a multidimensional vector. What would happen if I changed only one component? And from this formula, you can immediately see that if all of these delta x's are 0, the only thing that you're going to be left with is this one term, right? The corresponding alpha 1, remember, the derivative itself doesn't depend on delta x. The derivative alpha depends on the current position and nothing else, right? So which means that this alpha 1 is simply going to be the partial derivative of y with respect to x1, assuming all the other components are fixed. Make sense to everybody, right? And so we often represent it as, the dou y over dou xi, and then immediately this formula falls out, which is familiar enough for all of you, that the increment in y is simply going to be the sum over all components of the product of the partial derivative with respect to the component times the increment of that component. Right? Now this is important. We're going to use it all the time. Now terminology. This term, the derivative itself is a row vector, but you're probably more familiar with the term gradient. The gradient by definition, if you're representing the inputs as column vectors, the gradient by definition is the transpose of the derivative. So the gradient is going to have the same dimensionality as x itself. Okay? So having introduced all these ideas, I'm going to, in the next few slides, remember we're trying to minimize error with respect to parameters w, but I'm going to use more generic notation. I'm going to speak of some function of some variable x. Don't get confused. X is not to be confused with the input. It's just that I'm abstracting the problem out as some function y of x. Okay? So now let's look at the business of optimization. You want to find the problem of optimization, function minimization is that of finding the value x where f of x is minimum, right? So something of this kind. You might have a function of this kind. You have multiple locations where the function kind of bottoms out, but there's one location which is lower than any other location. That's the global minimum, and that is the location that we're trying to find. Now, if the function is a nice bowl, there's only one point at which the function bottoms out. So this is what you'd want to find. If the function is a hideous function, there are many places where the function has a local bottom. You want to find the best one, the lowest one, right? So now, if a function is bottoming out and it's continuous, it's decreasing before it hits the bottom. It's increasing after it hits the bottom. At the exact bottom, because it's continuous, you expect the derivative to be 0, right? So anytime in high school or college, if you were asked to find the location of the minimum of a function, the way you solved it, you computed the derivative, you equated it to 0, right? Turns out this is not enough. Why? Because there are two different kinds of locations where the derivative is 0. Both maxima and minima have 0 derivative. So here, for example, when the function is approaching a maximum, initially the slope of the function is going to be positive, then it hits a maximum, and then the function becomes decreasing, so the slope of the function is negative. When it hits a minimum, the slope of the function is negative because it's falling. Then it hits the minimum, and then the function begins increasing, the slope of the function is positive. So both maxima and minima are locations where the function changes its direction. These are what are called turning points. And the derivatives at turning points are always 0. So when you look at the derivative of the curve, you find that the derivative of the curve is going to be 0, both at maxima and minima. But then here is another property. So just saying that the derivative is 0 doesn't give you enough information. It doesn't tell you whether it's maximum or minimum. But then look at the derivative itself. When you're at a maximum, the function initially is increasing. It hits the maximum, and then the function begins decreasing. The slope of the function to the left of the maximum is positive. The slope of the function to the right of the maximum is going to be negative. So if you plotted the slope is going to be like so. It's going to go from positive to negative at a maximum. It's going to go from a negative to a positive at a minimum. So what is the slope of the slope? It's negative for a maximum and positive for a minimum. So if you computed the second derivative, you're going to get something of this kind. The second derivative is negative at maxima and positive at minima. And so this is a standard test that you ran in school. You first computed the derivative, then you equated it to 0 to find x, then you check the second derivative, right? Easy enough. So if you want to find the minimum of a function, you want to find, the way you'd solve it is you'd find the value x where f prime of x was 0. This is a turning point. Then you check the second derivative, right? But then things can get a little more complex than that. Look at a function like the one on top. There are 3 different types of locations where the derivative can be 0. In the first case, at maximum, the function is increasing, then it hits a maximum, then it decreases. Then you have the minima, the function is decreasing, it hits a minimum, and then it increases. And then you have inflection points. It's decreasing, then it takes a little rest, and then continues to decrease. Or it's increasing, then pauses for breath, then continues to increase. So at these places also the derivative is going to be 0, right? What is the second derivative at those locations, which are not really either maxima or minima? Now, if you look at that, if you look at the second derivative, if you look at the derivative, if you have a function of this kind, the derivative is initially, the slope is negative, the function is decreasing, then it stops decreasing, then it continues to decrease, right? So the derivative has gone from being negative to less negative to 0, but then it continues to be, goes back to being negative, right? What is the second derivative at that inflection point? 0, right? So you have, if you begin looking at the second derivative, it is positive at minima, negative at maxima. At inflection points, it's going to be 0, right? Now, what about functions of multiple variables? That was just for one variable. Again, you have the same kind of situation. You have a function of many variables. You're going to try to find the location where the derivative is 0. What I mean by the derivative is 0 is that, regardless of which, now remember, you can approach any point from many different directions in multidimensional space. Regardless of which direction you arrive at that point from, you would hit a minimum, and then if you continued, and it doesn't matter which direction you continue, the next thing that happens is you begin going back up, right? Or so the optimum is still a turning point, but then it has this characteristic is that shifting in any direction will increase the value. It's going to go up. And so when you're trying to find the minimum of a function, you're really trying to find the location of the input where, such that regardless of which direction you move in from that point, the function increases. I'll stop over here. We'll continue with this stuff in the next class. Questions?